Hi, welcome to the ZP Developer Zone. So we like to do this webinar every Thursday at 8 a.m. London time. And it's really answering questions that come in during the week. Some of them are of a technical nature, some of them are of a sort of technical commercial nature, but I'll sort of essentially just jump into it. And I put this slide up and say, don't forget, like if you're interested in electrochemical techniques and a bit of a background, there's a couple of free courses on the Academy. Don't forget that we do provide a certain amount of free questions and answers through our webinars. We also offer collaborations, and we do have these running mostly at the moment in I was about to say UK and Norway, but I realized that actually we've just joined a Horizon 2020 let's say implantable sensor project that's got a lot of European collaborators. We do offer jobs. We've just been hiring at from a local university in Norway called USN, and we also have our ZP Developer Zone, and we do have our workshops. Our workshops, I would suggest, are particularly pertinent today. We are holding them. There's a big one in September in Norway. We have them in Coventry. We have a workshop actually on neuroscience biosensors in Coventry as well. We do have a big conference that's running back to back with one of our workshops in Norway. We also have a workshop in France as well. If you see a link, then I've already put the link underneath the video. So if you go to this video on the YouTube channel, you should find all the links there. Just to say about the Scandinavian conference, I have put a link to it here. This is running on the 13th and 14th of September. And it's probably a good way to sort of meet us, but also there's a bonus because there's a workshop before it, so you can essentially spend 4 days with us and around us, let's say in Norway. 2 days for the workshop, 2 days for the conference. The questions that have come in this week, there's one on limit of detection with SPEs, limit of detection with screen printed electrodes, one on gold electrodes. We have a very good interaction with a group in the US that's got some of our gold electrodes. I'll comment upon that. And also about sensing in glucose and lactate in the sweat. And I'll come back to these questions in a bit. Just to say on this workshop front, all of these questions actually are really pertinent to the workshop because we do cover things like cyclovoltammetry in the workshop. We do cover glucose and lactate sensing in the workshop. And we do cover IVD, in vitro diagnostic development, and sort of point of care or point of need development in the workshops as well. And again, if you see a link, then I've already put the link underneath the video on YouTube, so hopefully you can find it there. Question number one, what's achievable limit of detection with an SPE? I'm going to show you some data where we do nanograms per milliliter. I'll say it, you really don't need to be spent in the long run. You know, at Zimmer and Peacock, we have a long background in glucose sensing, glucose strip manufacturing. So you know, when you get to volume in glucose strip manufacturing, and that's quite a complicated device, you know, there's the electrodes themselves, there's the formulation that goes down on top of it, there's a microfluidic channel that goes down on top of it. At volume, now this is millions, you get to between 2 and 10 cents. And I just heard the other day some, you know, that pricing at 6 cents. So I knew that my pricing in real terms, well, in relative terms, it's actually got cheaper over the years with glucose sensing, but the pricing, you know, is between 2 and 10 cents. That's what you can do with electrochemical sensing. I'll come back to these points a little bit. Gold screen printed electrodes. We are going to jump into the cyclovoltammetry of gold screen printed electrodes, and I'm also going to, as I say, discuss glucose and lactate sensing in sweat. I'll remind myself to say this during this webinar anyway, but if you are going to work on either glucose or lactate, start with glucose. The lactate materials, the enzymes associated with this are really expensive, so it's a really hard analyte to be learning your trade on because you've got an inhibitory problem, which is the cost of the enzymes. We can deal with it because we're a company, resources are fairly good, but I would say if you're really getting into this science and engineering, I would start with glucose. Now in the workshop, as I've already mentioned, we actually in fact, yeah, the workshop actually covers all these points anyway, but I'll move forward now. So I'm really dealing with question number 1 here, which is a lot of this question really, you must understand that when we answer questions, I do a sort of anonymize, if I think something sensitive, I'll leave it out basically. But they're really interested in the sort of limit of detection around small molecules. They mentioned cortisol, testosterone, and malic acid. Testosterone and malic acid. Cortisol, we're doing it in the nanomolar. Nanomolar is pretty equivalent to sort of tens of nanograms, hundreds of nanograms per milliliter. Testosterone, we are definitely doing that in the picomolar. It's 10 to minus 12. Malic acid, that's actually quite a high concentration, so you won't be so interested in it. It's what we call the micromolar. But I will show you some data where we're sort of distinguishing things like 5 nanograms per milliliter. Anyway, that will come up. How specific are they? Look, this is how specific a sensor is. Really, it's a systems level question. It's not a sensor level question. You can get specificity from the way you do the assay, the macromolecule if you use an enzyme or an antibody. The electronics or the assay that runs upon those electronics is also part of the assay. Is also part of the specificity, and also how you extract the information from the signal is also part of the specificity. So this question about specificity is really a system level. It's probably worth saying that in IVD space, glucose sensing is the kind of grandfather of in vitro diagnostics or point of care testing. There is an ISO standard for it, so you can just follow not just, but at least you've got a starting point by using the ISO standard for this. At ZP, our biosensors we do antibody, aptamer, receptor, MIPS, molecular imprinted polymers, ionophores, enzymes, and sometimes the electrodes have no materials on them. We get specificity from the assay, the way we actually run the electrochemical assay. But for us, because we're not academic in terms of we're agnostic, we're not trying to push a particular technology. When you have an academic career, you have a thesis and you always push that thesis. My thesis might be, that I really like aptamers, and that's what I'm always going to do. Whereas ZP, we're pragmatists. I say we're not academic. I realize I do have an honorary position at a university, but we're definitely sort of, let's say, more sort of pragmatic and industry focused. Transduction mechanisms. You'll see that with all these sensors, actually, we're using chronoamperometry, cyclovoltammetry, impedance spectroscopy, potentiometry, differential pulse voltammetry, square wave voltammetry, and we're also doing some field effect transistor work as well. So we're agnostic on this. And in fact, we will use all of these methods and find out which one gives us the best limit of detection, if that's the key performance indicator that we need. Are our sensors reusable? Theoretically, our sensors are reusable. I won't recommend reusing, because the only time I would recommend reusing a sensor is when you've got a benchtop blood gas analyzer where you have things like calibration solutions and wash solutions. If you're trying to make a low-cost point-of-care device, reusable is not a good idea, because you then have to sort of prove that you're going to be able to clean this electrode. Whereas, unfortunately, I understand the carbon footprint, but if you dispose of it, then you get away from that problem of proving that you've cleaned it. So our electrodes our sensors are often actually reusable. Whether we reuse them in that sort of point of care or field test, that's very debatable. We do have graphene electrodes, gold electrodes, carbon electrodes. Again, we're pragmatic. We'd actually try all of them and see which one gave us the best limit of detection. But we have them. What's nice about ZP is we have all these things on the shelf, so we can actually, rather than it being a sort of a big decision, you can just pull them off the shelf and try them. In terms of limit of detection, I'm going to show you something today that's picomolar. So femtomolar is probably 10 to the minus 15 is probably the limit of things, but picomolar is possible. It's interesting actually, because at ZP we got a whole stack of technologies in terms of electrodes. Electrodes get turned into the sensors. We have electronics, we have apps, and we have a cloud where we can send the data. So whenever I see this kind of comment about calibration, if you're going to do a point of care or point of need device, you should not ever be doing calibration on that device in the field. It's not going to make for a low cost device, and I would super strongly suggest and the reason that people try to do calibration in the field is because they have irreproducibility on the electrode and therefore the sensor upon the electrode, whereas we don't have irreproducibility. We actually have really good reproducibility. So never do calibration. Calibration should be in the factory, not in the field. Yeah, we do have a good price on our electrodes, and we should be, and I will show today at least some strong evidence that we can get down to low concentrations. And we can integrate with other rapid diagnostic technologies. Whether you need to or not is a sort of, it's really a consulting question. So for example, our glucose sensor, I mean, the glucose wasn't asked, but I brought it in anyway. I mean, glucose is the kind of high concentration guy, that we're actually doing things like 1 millimolar. So glucose and lactate are not so applicable to this question, but actually it is applicable to question number 3, which will come up in a bit. And it's probably also worth pointing out that the questioner in question 1 should also have a look at the answers in question 3 as well. Now, malic acid is actually getting closer to things that we're actually testing down at 10 micromolar, for example. So malic acid is getting lower. This is testosterone. This was definitely asked by the questioner, and here we're in the picomolar concentration. This is really quite low. So something that I probably didn't point out a little bit was actually that some of this data is chronoamperometry, and then some of this data is actually impedance spectroscopy. So it makes the point earlier on that actually we use a technique that gives us the best sensitivity. We don't go in there with a mindset that one is better than the other. We have, I have opinions, and I also have some data on those opinions, but you've got to stay open-minded on which analytical technique that you will actually use. And of course, at ZP, we have a lot of experience on this. This is cortisol. This is down in the nanomolar, which is not so far off this nanograms per mil. This is an immunotype sensor that we made. Again, I've just changed from chronoamperometry to impedance spectroscopy, and here we are doing things like, what's nice about this is there's 3 electrodes there that we're testing 3 different electrodes at 5 nanograms per mil, 3 different electrodes. These are 3 different electrodes at 25 nanograms per mil. This is 3 different new sensors made tested at 50 nanograms per mil and 75 nanograms per mil at the end there. So it tells us something about the underlying repeatability of our electrodes. So that underlying repeatability of electrodes is what helps with us with our limit of detection. And it also helps us with this ridiculous thought that, you should not be calibrating devices, I would say, in the field. There's no need for it. When you're calibrating in the field, it means that you have a manufacturing irreproducibility problem, is often the case. Limit of detection is a kind of interesting question because I said it already, but I mean, one of the things that's very strong at ZP is actually our data sciences team. And we do have a very bespoke system called Julie. It's a cloud system. We upload all our data to Julie. And I made a video for a different reason a few weeks ago, but actually I just showed that you can have the same set of data, and whether you, depending on the sort of analysis on that data, you can actually affect the limit of detection by, in this one it was, I wouldn't say it was the best data in the world, but by changing my window of integration, I was able to actually increase the limit of detection, or when I say increase, I was able to improve it by a 10x. So I just want to say that, that's why I kind of say that, limit of detection is really a question about the entire system. And it's also a question about the way that you analyze the data. So we can make a good sensor look really bad through doing the wrong algorithm, or we can make a not very good sensor, well, an okay sensor be much better through the algorithm for information extraction. And the nice thing is we have all this kind of automated, because we've been building this cloud system in fact for 8 years and 10 months. So I'll go a little bit faster now anyway. Specificity is really an applications question, because whether you're specific or not is based on the sensor, based on the system, and based on the matrix in which you're in. So I would say you've got to be very careful of that question. But in fact, to be fair, there are ISO standards out there in the in vitro diagnostic point of care world. This one's specific to glucose, but you try and, we could find an ISO standard that was closest to what you're trying to do. At ZP, we're very agnostic on the sort of specificity part of this. What I mean by that is we can use enzymes. I quite like enzymes. They give a strong signal. They're very active. Aptamers, I like aptamers. We do have a really good sort of bioinformatics team that designs aptamers. depending on what the target is. I like them because you can design them and then the manufacturing is really reproducible. We do use antibodies. If I was given a choice between going the aptamer route and the antibody route, I'd probably choose the aptamer route these days. Receptors, if we were doing pathogens, then we would be using receptors. If we were doing ions, we'd be using ionophores. So specificity comes from these choices here, but also you've got to look at specificity being a total systems question, including what the actual sample is. You can have, for example, if you're testing saliva, whether you're sensitive or not sensitive to hemoglobin becomes less relevant. Whereas if you're testing in blood, if you're sensitive or not sensitive to hemoglobin becomes a lot more relevant. So it's really an applications question as well. I've already said this, but in fact, at ZP we do, these immunosensors, but there's also people are using MIPS as well, which is a kind of, it's an artificial antibody. Are they as specific as antibodies? No way are they. But at ZP we actually do these, and we're the only people in the world who actually have a decent way of scaling this kind of technology. When I say scaling it, manufacturing it. So if the route is molecular imprinted polymers, people can make these kind of singly or parallel on potentiostats, but actually we do have robotic systems for making MIPS at larger scales. So we're pretty good on the MIPS as well. Whether you do a transduction by current amperometry, cyclovoltammetry, impedance, this is really covered in our workshops, but all of these techniques are active at ZP, and we are implementing them on our own electronics. So, what's the size of electronics that you need for this kind of work? It's the size of the tip of my finger. Whether you do amperometry, voltammetry, potentiometry, impedance spectroscopy, we often mix techniques as well, by the way. We might look at the assay in several ways. It just makes for a more accurate assay. And then we can implement all of that on our electronics as well. So, and the other one that's sort of entering our arena at the moment, as I say, is field effect transistors. Field effect transistors and biosensors or electrochemical sensors, there's no real, people seem to think there's some significant difference between these technologies. There's not. It's whether you have a electrochemistry background or an electronics background, depends on which one you actually choose. I like electrochemical techniques because there's a lot more of them. We've got a lot more parameters to play with. That's why I sort of prefer electrochemical techniques. It's a considered point. It's not just based on historical. I mean, we will choose things that, like voltammetry, depending on, we generally find that it's known by lots of people who follow our webinars that cyclovoltammetry is the least sensitive, and if you want to get a sensitive assay, differential pulse and square wave voltammetry are our kind of preferred methods. When it comes to electronics, at ZP we have a really good. Welcome to so let me just mute that. We have an existing platform that's really good for converting ideas into minimally viable products within really weeks. So as long as the sensor and the assay exists, then we can translate it onto our platform, very quickly. Let's say. I mean, our platform has, so if you have a particular sensor in mind, first of all, we would put it on one of our low-cost electrodes. This one's quite nice actually, because you can see here that we put a simple microfluidics on there just to kind of hold the sample in place. We have the meter itself. The meter connects to an app. And it's really important because what you'll see is with these kind of videos, we're never doing the calibration on the device. The calibration's all taken care of through the firmware, and also through the way we do repeatability in terms of factory calibrations, or manufacturing within the factory, if I could put it that way. So we have our apps. We also have an added bonus that if you were doing some sort of test and you wanted to kind of get control over the raw data, all the raw data would immediately go to our cloud system, and actually we have a capability of sending that data to another cloud system. So this is really a set of technologies that describes an MVP, a minimally viable product, and we can very quickly turn assays and ideas into what we call a minimally viable product pretty quickly. And then people can actually start testing it with themselves to start with, and then testing it with outside stakeholders. I should say there's a link here, and hopefully I've put the link underneath the video as well. Are our sensors reusable? I did touch upon this earlier on, that theoretically our sensors are often reusable. the big problem I have with that question is you've got to have a cleaning procedure and you've got to prove that you've cleaned it, especially with biological samples like blood, urine, tear film, saliva, sweat, you know, all these kind of things. Really, I'm not sure about reusing them. I think it's unfortunately, I understand the carbon footprint. So at ZP, we are kind of obviously thinking, you know, about the materials of construction, because, you know, we do understand that there's going to be a moment where they're going to say, okay, medical diagnostics industry, you can't be part of, you know, increasing the amount of disposal in the world. So we do understand that. But at this moment, the idea that it's not a great idea to build a product, especially where a drop of blood's going to go on it, because once you have to start washing it and recalibrating it, etc., you're building in cost to your device. You're probably even building in a larger carbon footprint, because you're going to have a lot more plastic to deal with that. But realistically, I mean, our sensors are reusable. This is a glucose sensor. That's not so much we've been reusing it, but we've been using it continuously for 125 days. So it does give you a sense of, and in fact, this sensor's still running. So it gives you, and again, if you see a link, you can find this on the website anyway. Working with ZP, I think we're pretty experienced now. We're 8 years, 10 months into this. We are ISO 13485. We have a strong team. We have 4,000 square meters of manufacturing, so you can consult with us. You can do micro mini projects with us. You can do proof of principles with us, and you can also do first phases with us as well. So I've put all those links underneath the video. Question number 2 is a good one. It comes from some people that we've been working with for, I would almost say, I've known them for more like 15 years, but actually we're working with them for about 7 years. They have one of our older models of screen printed electrodes. I say that because these days I'm really trying to get everyone onto, we call it kind of our hyper value platform, and I put a link to our hyper value platform there anyway. But they were kind enough to send me through a bunch of data. They're using ferricyanide to characterize their sensor, and this is kind of, you know, this is a new sensor that we've sent with recent, and they report here that there's, when I say burning, you'll see in a bit what the burning is. And I looked at their data, and this one, it has no burning, and they report that it has no burning. And I'm very careful to note the potential at which they went to here, which is 0.5 volts. And they're in quite, you know, they're in 0 millimolar HCl, hydrochloric acid, so no probs. This sensor is really the same thing, if I can say that. New sensor, 10 millimolar HCl, but again, they only went to 0.5 volts, and there's no sign of burning on the sensor. They call it burning, I think it's oxidation, and there's no sign of, there's an extra peak you'll see in a bit, but it all looks pretty clean. Really nice cyclovoltammetry. And realizing how, I'm very proud of our electrodes, I'm realizing how similar those two sets of data actually are, which talks about our repeatability in terms of electrodes, which I will touch upon in question number 3, but it's also relevant to question number 1. We're really quite good at manufacturing and repeatability, which really helps with limit of detection. This one, they had no graph available, but they're basically now reporting that they do get some, they say burning, call it scorching, call it oxidation, but they report that. It's interesting, see, they actually just went to 0.6 volts. So they went from 0.5 volts, now they've just increased that voltage a little bit. This is another sensor, but again, they're at this 0.6 volts, and this time they get this little kick up at the end here. I have a feeling that the strongest correlation between, let's say, this, they call it burning, and the burning or not burning is when you get this little kick up. And I'll give you some references to papers on this as well in a short while. So they went up to 0.6 volts, they get some burning, and then they have that extra little kick up at the end of that voltammogram there. They're in 5 millimolar HCl, no props. Okay, sensor number 4 I feel like is in a really similar place, except what they did is they seem to have modified the counter electrode here. So this one's I would say interesting. It's not so relevant to ZP because their modification is their modification, but it's interesting to see that they've modified this electrode fine. They get that kick up, and they're also using that 0.6 volts. So again, I think there's a correlation between going to 0.6 volts and getting that, they call it burning. similarly here now, new sensor, no burning, but actually they only went to 0.5 volts. Well, they say little or no burning. I mean, so I suppose it's interesting actually because their signal interpretation, little or no, is sort of, it's not like it's not a quantitative result, it's a qualitative result. It's a sort of slight opinion, let's say. This one is the same. They say here little or no burning. See, so I mean, I'm just, it's sort of like, see, because you get this one. I think this is the one that kind of, I have this theory, and this is the only one that doesn't fit my theory. But then I'm realizing that when you're making sort of decisions like this, you need statistical numbers. We would sort of, we would be testing 30 electrodes and actually saying, okay, because it's not unusual to sort of have, one sensor doesn't quite fit the pattern, but then the other 29 do. So be careful. So this one doesn't, because what it says is, actually they say little or no burning. So they're a little bit ambiguous on it. I see that kick up. So I would actually have said, yeah, that would have given you a burn. But they say little or no. Well, that's sort of an opinion. And they also say it's the old sensor. So we've given them a couple of batches. And so they're trying to say, well, is this new batch the same as the old batch? I would say it was, to be honest with you. And I would say that some of your sort of reporting on burning is a little bit, on the edge, where there's little or no. It's like, yes. So your analysis is not criticism. It's qualitative and, a little bit subjective, I would say. This is an old sensor, but this time they've only tested to 0.5 volts, and they say little or no burning. I'm sort of building up this thing that actually, what am I thinking? I'm thinking really that what's your assay? When you run your assay, are you running your assay in the window minus 0.6 to 0.5 volts? And when I say your assay, you're finally making some sensor upon the top of these electrodes. Because if you're actually using this sensor in the range 0.6 to 0.5 volts, don't test at 0.6 volts. I think 0.6 volts is a bit of a problem for you, and I'll show you some literature precedents for that as well. But I'm really not seeing, I think the strongest correlation between, let's say, burnt and not burnt is whether you scan positive or 0.5 volts, i.e. you go to 0.6 volts. I think old and new are actually doing the same thing. I mean, your kind of reporting on old is little or no burning. I mean, it's a bit of it's a bit ambiguous. Now, why do I think that you're getting this burning? I think it's because it's known that gold will oxidize, and I think it is actually helped by chloride anions. If you're not running your assay at something like 0.6 volts, don't include 0.6 volts in your kind of screening. This is kind of a quality test that you're doing, because it's not applicable to the way you're actually going to do the assay. I also have a suspicion that pH does help with this oxidation of gold. And the oxidation of gold is a sort of known phenomenon. So I was very quick when I went and, I just went looking for something that agreed. Let's say I selected this because it agreed with my theory. So be careful of that. But I did find a quick paper that kind of said, yeah, chlorides and gold, chlorides help golds oxidize, and it happened to be in quite a similar position to where I think you're just stepping into this 0.6 volts and just getting this slight oxidation. It's not the worst thing I've ever seen in my life, and I actually think, it's my opinion, but don't worry about it, to be honest with you. I did put everything in the table, so I have done this kind of, fairly systematically, and the only one that doesn't quite fit with my theory, I would say, is that you report on one sensor at 0.6 volts and you kind of say little or no burning. So I would say either just move forward, or if you really think you've got a problem, you're going to have to do a lot more testing to really get statistical numbers. I said 30 earlier on, but we are doing testing at quite a lot of scale, I would say. This is question number 3. Question number 3, somebody's coming in, they're interested in doing lactate and glucose monitoring in a continuous manner, and it should be wearable. So at ZP, it's probably worth saying that I've spent at least 15 years making continuous glucose sensors. ZP itself has been around 8 years, 10 months, and the whole team is very sort of drenched in this CGM world, and including lactate as well. So they're saying that we make electrodes, and we also do modified electrodes. I'll put some slides up on that. Are they based on Prussian blue? We do have modified electrodes with Prussian blue. We also have methylene blue. We also have Medulla blue. I'm also going to put some links to that as well. Are we using platinum or carbon? I I actually I tell you at the end of this in a few slides how to make a glucose sensor. So there you'll see when you click the link that I'm recommending a platinum electrode. How quick can you have 100 or 1,000 electrodes? 3 to 4 weeks is our typical shipping time. We also do the microfluidics. So you need sort of two types of microfluidics. One that's a sort of wearables microfluidics, almost like a sweat patch. We do have that. And you also need a sort of formal microfluidics to do benchtop testing, and we also have that as well, and I will put some videos to that. It's probably worth saying that we do a lot of app development, and with continuous glucose and continuous lactate monitoring, you need to, it's the same as question number 1, you can't be doing calibration on the device. In order to make a CGM, it's probably worth just saying that most companies that make reliable CGMs, continuous glucose monitoring, in their early rounds of funding, they raised about $100 million US, and then it's not unknown for them to have spent $500 million by the time they actually get to market. So just be careful what you can achieve in CGM, continuous glucose monitoring. I mean, ZP, we're very involved in these large companies and doing these kind of projects. So it's first-hand experience what it takes. So we do have mediated electrodes. Quick link and you'll find it. We also have screen printed electrodes. I'm going to put 3 links here. They're all worth having a look at because this also is relevant to question number 1. Limit of detection for us comes from the fact that we do have really good repeatable electrodes. We do have really good platinum, really good gold, really good carbon, and really good graphene. I'll put a link to that as well. And if people want custom electrodes, we also have a kind of a really good low-cost manner to get them customized electrodes. So I do have a link to that as well. Now, CGM and continuous lactate monitoring, they are definitely covered in our workshops. There is a workshop on the 11th to the 12th of September. These are very, very practical workshops. You're in the lab, you make your own sensors, you test your own sensors. So I think a lot of the questions that came in on number 3 are really, the short answer is come to the workshop. But you construct a glucose sensor there, you test a glucose sensor, you test an oxygen sensor, or construct, you test. You construct a lactate, you test the lactate, you do continuous pH. And that's just the first 8 points. I thought I can't be bothered to go through all of this, but the workshops, there's a link, and they're well attended, and there's quite a buzz at these workshops. I think people come away very satisfied. So there's the workshops. Back to the question itself. At ZP, we're extremely good at doing wearable sensors. We have transcutaneous sensors. This is literally a picture of our website, so we do sell those. We have microneedles on our website. We do sell those. We do have a sweat patch for non-invasive. We do have that. I'll link to it in a minute. We also have implantable sensors. The entire package goes in the fish in this particular case. Side note on electronics. It was relevant to question number 1 as well, that our electronics are the size of the end of my finger. We don't lose anything by shrinking the electronics down. This is actually a glucose sensor that's being tested probably in the clinical range on a large set of electronics, or a larger PCB and a much smaller PCB, and we really get the same results, so we're pretty happy with that. Our experience on CGM, which is also relevant to continuous lactate monitoring as well, is that, you know, we're on these, not on these, but, you know, this particular product's had easily €1 million spent on it so far. This is the actual electronics package itself. It's got a transducer in there for sending out the data, and this is the electrochemical sensor as well. This actually gets implanted. This fish is not dead, it's anesthetized, and we actually implant them in the fish. And this is the fish swimming around after that implantation. So you've got to have pretty good technology in order to do this kind of work. You've got to have pretty robust technology. So we're pretty lucky to have, not lucky, but we worked hard, and this is the continuous data that comes off it. So we're pretty pleased with that. This is a bit more relevant because actually at ZP we have probably the world's largest range of off-the-shelf biosensors, including glucose and lactate. And we also have a package. Well, we're very good, if we're on a proper project that's properly funded, we're really good at turning these sensors into an entire system, let's say. And then really good at actually calibrating as well. And with glucose, you can calibrate against off-the-shelf products. So we're pretty good at making wearable sensor platforms, if I could put it that way. And I put a link to this as well, because there's a whole sort of video about this. Particularly on sweat. We do have a sweat patch, which is available on the web store. And we have done, so for example, continuous lactate monitoring, where we have electronics. We have a lactate sensor inside of the sweat patch that I was just showing you. We have Bluetooth connection, and we're able to get the data out then to a in this case it was a PC, and by watch, so we had a sort of a timeline here, concentration. So we started riding the bike, then the guy's perspiring, but even though he's perspiring, we get no lactate signal. But as soon as he starts straining, that's when the lactate is coming, and that's when you get the kind of lactate signal. It's really interesting because you always have this dip in the lactate profile, and I'm very, I'm pretty good terms with the Joseph Wang team down in UCSD and people like that, and they have exactly the same dip in their data. So I think it's due to glucagon, which is stored, I think, near the liver. So there's a sort of physiological reason for that. But anyway, we've got just a comment, by the way, and I've said it already. If you've got a choice between learning your science and engineering on glucose versus lactate, go for glucose. It's much lower cost to kind of get into this kind of tech. Just the price of the enzyme. So, in the workshop, we do cover how to make a lactate sensor, how to make a glucose sensor, and how they work. I just want to say, if you're trying to try and make a wearable biosensor, here's a whole bunch of links about the electronics. There's a data sheet in there, etc. In terms of advice, just go for a glucose rather than lactate. If you're going to be doing, I just want to mute that for a second because that's Andre speaking away. I do put a link to this video. We do show a flow cell which will help you do IVD work, in vitro diagnostic work. I shouldn't say IVD work. I should just say for testing on the bench rather than testing on the people. And we do have some tech for that. And I should just say, yeah, there's a link to the video. There's a link to the product that's actually been discussed. If you're going to start with glucose rather than lactate, but you will find some of these links will also show you the lactate as well. So you need a potentiostat, you need connectors to go between the potentiostat and the sensors. You may need electrodes. So I've linked to it there, and I say it's the platinum. I also tell you where to get the enzyme, and I also tell you where to get the barrier layer as well. If you really want to see how to do this, again, come to the workshop. But these are all the materials that you would need. So let me look at the time. Okay, right. So question number 1, what's achievable limit detection with an SPE? I have shown you data today where we're definitely in the nanograms per mil range. So I think that answers basically the question. Gold screen printed electrodes. I've got a feeling that the evidence that you really have a big difference between what you call old and new batch, I think it's pretty marginal. I think the biggest indicator of burning is that going up to 0.6 volts. And then actually I have hopefully linked to you that we've actually done lactate in sweat. If you ever do lactate in sweat, Zimmer and Peacock, you will find those pages, and all the links I've definitely put underneath the video as well. Right, so I'm going to have to rush off to Cambridge University today, but here's some links, and contact us if you've got any questions, and yeah, we're always happy to give these detailed answers. I realize I've been talking for 38 minutes. I talked fast today because I knew I had a lot of material, and there was only 3 questions. So, okay, I hope that's useful, and I do appreciate the questions. If you've got questions and you're following along, send them to us at zimmerpeacock.com. Contact us, or contact rather. Okay, thanks very much.